Morning. There's not very many people here today, comparatively speaking, which is bad because it's like the first time we're doing anything challenging. So you're in the right place, is what I'm saying. Okay, so what we were doing last time is we were talking about osmosis, right, as a transport mechanism. And osmosis is a transport mechanism that basically is diffusion of water across a membrane, right? Okay. And so we were talking about a couple of different instances in which osmosis is relevant to the human body, like when you drink salt water or use a normal saline solution. So first thing I want to do is just start with like a video that actually shows you guys osmosis in action. This is with red blood cells or erythrocytes. What's the inherent shape of a red blood cell? Yeah, it's a biconcave disc, right? Concave on both sides. FYI, maintaining the shape is really important for a red blood cell, not just for hemoglobin, but also because the capillaries, the smallest capillaries that you have, are hardly bigger than a red blood cell. So if you change shape dramatically, they can't really be transported. So this one's going to show you just the osmotic effect of different solutions on red blood cells. This is in a capillary. This is a big capillary. You have some capillaries that are only a single cell wide. And then what about normal saline? What do you predict is going to happen to the red blood cell in normal saline or an isotonic solution? Should be able to maintain its shape, correct? Okay. Hypotonic solution, prediction. Swell, exactly. They don't function when they swell. You break the cytoskeleton when you swell, and eventually you can actually cause hemolysis. So they become spherical in a hypotonic solution. That's why you don't want to shoot anybody up with straight water. Hypertonic solution, prediction? Shrink. Crenation. And crenation will affect red blood cell function as well. They actually won't be able to pick up and drop off oxygen and carbon dioxide. So that's called crenation. Okay? Is that okay? All right. So we will be talking about osmosis multiple times throughout the semester. We're going to run into it, of course, in getting water in and out of the kidney. You're going to be dealing with a lot of osmosis, and we're also going to be running into it with capillary function. So I'll apply it over and over the semester. Okay, so the next thing that we're going to do is we're going to move to mediated transport systems. In order for you to grasp what I'm talking about, I need you to understand what I mean by mediated transport systems, because some textbooks vary in what they mean. So with this textbook and with me for the rest of the semester, if you're using a mediated transport system, you need a mediator. So if you've been through a divorce, you know that sometimes you can't be in the same damn room with each other without a mediator in the middle to help make things happen. So a mediator is someone who actually helps with the transport process. And the mediator is going to be a carrier, not a channel. Okay? Some textbooks include channels in mediated transport. This textbook does not, and I don't. Okay? So a mediated transport system will use a carrier. Remember that a carrier does something specific. It's involved in the transport process. It has a binding site, changes conformation, exposes the binding site again, changes conformation. So before we go any further, I want to make sure that you guys can do comparison contrast between two kind of similar things. So what we're going to do is we're going to talk about two different transport proteins and make sure that you can delineate and differentiate between the two of them. And they are, this first one we learned about last time in detail, and this was simply a ligand or chemical gated channel, right? And it had a regulatory site right over here which bound a ligand, right? And then when that bound, what happened is you opened it, and then something went in or out, really. Does that make sense? Okay, so this is a ligand-gated channel. So the important thing that I want you to think about is look at this picture because it's better than I can draw, but I'm also going to draw you a bad picture up here. I want you to look at the difference between that and this. And this is a carrier. So what a carrier is, it has a shape-specific binding site, but it has a shape-specific binding site for the transported molecule, or it could be an ion, but transported molecule, okay? So this is the transported molecule right here. And then what happens is when the transported molecule binds, the carrier actually changes conformation and dumps the transported molecule. Okay, so somebody in your words, oh, by the way, this is called, this is a carrier protein. So somebody in your words, tell me the difference between a ligand-gated channel and a carrier protein, because you can't use those terms interchangeably. What's the difference?
One of them uses something to bind to it, let something in, and the other one, when it binds, it lets in.
Yeah, so that's a really important thing. With this one, the thing that binds to the shape-specific binding site is actually the thing that's carried. Yeah? Okay. With this one, the thing that binds to the shape-specific binding site, this might be acetylcholine, which opens a sodium channel. I had no intention of transporting acetylcholine, right? That makes sense? Can you see that these will have different transport rates too? Once you open this one, sodium just goes, right? What does this one have to do? Every single time you bind, you change positions, you have to rebind, change position. So which one's slower? That one's way slower, right? And it's also shape-specific about the thing that it's transporting. Okay, so hopefully today I can get you past the idea that channels and carriers are interchangeable, because they're not. They're not the same thing. Okay, so let's talk about this in more detail. So what we are seeing here is mediated transport systems have shape-specific binding sites for the thing they're carrying. Yes? Okay. In addition, it has a shape-specific binding site which will limit the transport rate that it can carry something. So I want you to think about this. We had one of these proteins, right? One of these carriers, and this is a carrier. One of these carriers and 20,000 triangles up here, right? It doesn't mean that you can increase the transport rate, right? It's going to be subject to saturation, just like an enzyme. Remember when we saw that enzymes were subject to saturation? Because they had shape-specific binding sites, right? They were subject to saturation. This is also true with carrier-mediated transport. Basically, if I was transporting glucose, I cannot transport glucose any faster than the carriers can transport glucose. That makes sense? So this looks very much like that saturation graph that you had with enzymes, only notice that the y-axis, instead of being enzyme reaction rate, is actually net flux, which is the speed of transport, right? So as the concentration gradient goes up, the transport goes up until what's happening here? They're full, right? It's saturated, right? So that will be important to you. It is the reason why, for instance, if you are a diabetic, you are going to end up with sugar in your pee. Because you try your damnedest to take all of that sugar and absorb it back to your bloodstream, but your glucose transporters are subject to saturation rate. It's also the reason that you, after Halloween, if you had a good one, and I was like, oh, I'm only gonna eat like 2 Reese's. It's literally never happened, right? The little Reese's. The perfect ratio of chocolate to peanut butter. The big ones can suck it. The little ones, they're awesome. But it's also the reason why you, after Halloween, will have sweet pea. There's a limited quantity of glucose that you can actually absorb at any time. And like a lot of it, like you absorb it and then it gets pushed into your kidneys and your kidneys try to reclaim it, but they're subject to saturation rate. So you just end up peeing it out. So basically what I'm telling you is it's better to go on a sugar bender than eat sugar every day. Because you like are just limited by how much you can absorb. But don't do that. Don't go on a sugar bender. Be all healthy and crap. And crap. Okay, so it's subject to saturation limits. Okay, so now, mediated transport is what we're talking about, and it's always going to use what? Channels or carriers? Carriers. We're always going to be using carriers. Now let's do the simplest of mediated transport, which is this one that we've been looking at right here. Oops, sorry, this one. So this is a mediated transport mechanism called facilitated diffusion. Okay? All it is diffusion that can't go through by any other mechanism. So I'm going to diffuse glucose from outside a cell to inside a cell. This will be facilitated diffusion if I just tell you one piece of information. If I just tell you that glucose has a higher concentration in the extracellular fluid, then this is an example of facilitated diffusion, right? Because it's moving in, okay? But remember, you always have to defend if you are going to use an expensive or slower transport mechanism. So let's go back a little bit and talk about why glucose can't diffuse straight through the cell membrane. It's too big, and what about its solubility? It's a sugar. It is what soluble? Water soluble, not lipid soluble, right? Okay. Why can't it go through a channel? It's too big, yeah? So plan C, right? If you tried straight through and you couldn't get through, and then you tried a channel, which would be faster, right? And you couldn't get through. Plan C is a carrier. And if the high concentration, low concentration, this is called facilitated diffusion. It's basically, I'm going to help you diffuse straight through the cell membrane, but your concentration gradient already favors it. So what happens is you bind to glucose at high concentration, you dump it. You bind to glucose at high concentration, you dump it. A lot of people are in the habit of thinking that that always requires ATP. It doesn't. It's just diffusion. And here is how it doesn't require ATP. The binding of glucose changes the shape of the transport protein so that you end up dumping glucose. The dumping of glucose changes the shape of the transport protein so that you re-expose the binding site, right? So it's slow and it's clunky, but it's not energetically expensive. Right? It's still just diffusion, okay? So that's called facilitated diffusion. It's moving larger water-soluble molecules, not huge ones, but mid-sized, across a carrier down their concentration gradient. No ATP is required in order to do that. Okay, so this is, by the way, a common mechanism of moving glucose around and also moving amino acids around, and those are the mid-sized ones that we talked about. Okay, so now we are ready to do something that you've seen before, but I want you to be able to build it this time, so we're going to kind of build it slowly. Primary active transport also uses carriers. All of these that we're talking about are going to use carriers, but I'm going to use a carrier to move something against its concentration gradient, okay? So basically, it's like trying to get water to go uphill, not downhill, right? And if you want to get water to go uphill, what do you have to put in? Energy. Energy, yes, exactly. So I don't care what you're moving. I don't care if it's tiny. I don't care if it's charged. I don't care if it's big. Doesn't make any difference. You still have to put energy to get it into going uphill, right? So in order to get something to go from from low concentration to high concentration, you are going to need a carrier plus ATP, which is what you call a pump. That makes sense? Okay, so let's talk about a metaphor, and then we will talk about specific examples. A metaphor of primary active transport. The effect of primary active transport is that I end up accumulating something on one side of the membrane, right? Diffusion goes over time like this. If you do diffusion over time, you end up like this, right? That's just diffusion. If you do active transport over time, you either start out like this, and you can stay like that, even if you're leaking, or what if you pump faster? If you start out like that and pump faster, can't you accumulate even more of a concentration gradient? Right? Does that make sense? Okay, so with active transport, what you're going to do is you're going to get a net accumulation of whatever on one side of the cell membrane, right? An accumulation of particles on one side of the cell membrane. But as soon as you stop putting energy in, it's just going to diffuse straight back out. So the metaphor that I like to use is that, have you ever seen anybody take like a 24 balloon bouquet and try to get it into a teeny tiny hatchback car? It's hilarious, right? So you take this enormous balloon bouquet, because remember when your children were 3 and you did these elaborate birthday parties, and now you're just like, here's a gift card. You're like, I wore myself out on the superhero birthday party. So you got this enormous balloon bouquet, and you open up the hatchback, and you're starting to put the balloons in, right? And you are the carrier, and this is the ATP, right? So you're trying to put it in. As soon as you stop pushing, what happens? It goes straight back out. And then some yahoo, probably one of your children, left 2 windows open, right? So how do you accumulate them despite the fact that they're constantly leaking out? You're pushing, you're pushing, you're grabbing, you're pushing, you're pushing, you're grabbing. That's how you get an accumulation. If you stop the pump, if there is any opportunity, the thing will leak right back down its concentration gradient. So in order to maintain an accumulation on one side of the membrane, you generally have to put in a boatload of work because diffusion wants to do the opposite. Okay, so let's run into arguably the most important example of primary active transport in the body. So you are going to use a carrier, which means it's going to be shape-specific, right? Right? Shape-specific binding site. And you're going to require ATP. And the net effect is going to be an accumulation of stuff on one side of the membrane, right? Okay, so I know you've learned this one before, but you're going to have to build it from scratch this time. This is called the sodium-potassium pump, or the sodium-potassium ATPase pump, or the sodium-potassium exchange pump, or the sodium-potassium countertransport pump. It doesn't matter. It's the same damn pump, regardless of the fact that nobody can decide what other word to put in there with it. It's the same pump. You've got it on every single cell in your body. Some of your most energetically expensive cells have hundreds of these. These things are so damn important that in your electrical tissues, you use 40 to 60% of a cell's ATP just running your sodium-potassium pumps. So what we're going to do today is we're going to build to the point that you start to see why the hell they exist and they're worth the money. Okay? Not just what they do and which direction they go, but also putting the whys together. And I've got an animation for you after we build it. So what we're going to do is we're going to talk about the sodium-potassium pump, and we're going to basically start to build a cell, the important parts, and we're going to add in things and make sure you understand each part when we add it in. So we're going to start with a typical cell, and a typical cell, this part you may have memorized before. If you didn't, you'll need to. But of course, a typical cell, we've got ICF, and we've got ECF, and you already knew that. But some of you may and some of you may not know the relative concentrations of sodium and potassium in the ICF and the ECF. I'm not looking for numbers, I'm looking for high versus low. Does anybody know where sodium is high? No? Okay, so sodium is relatively higher in the extracellular fluid, and that's homeostatic compared to the intracellular fluid. Sodium is relatively lower. Potassium is the opposite. Potassium is relatively high in the intracellular fluid and relatively lower in the extracellular fluid. Please note that they're both positively charged. You have lots of other crap too, but we just can't talk about it all at the same time, right? So this is important, and keep it in mind because this is homeostatic for a cell, okay? Does that mean it never changes? No, your blood pressure changes, but what do you have to do when it changes? You have to put it back, right? Okay? This is homeostatic for a cell. You are going to change the living hell out of it in nervous system and cardiovascular system and muscles. But you always have to put it back, right? So that's homeostatic for a cell, okay? Doesn't mean it's like unchanging. It means that this is the ideal that you're going to have. Okay, so here is the problem that I'm going to create for you, and then we're going to talk about how you do the solution. So what I have is I have this, which is my ideal, but then I have something that is constantly working against it. And your question, your logical question would be, why the hell do you have these? And you're going to have to just trust me. It's going to take me a little while to build to why you have these. But let me tell you a truth. This is what I want to keep. And some yahoo, probably one of your children, left the damn windows open. This is a sodium leak channel. Okay, put in a leak channel. Where's sodium going to leak? Which direction? Look at it. It's going to leak in because of what? Yeah, diffusion concentration gradient, right? From high to low. Does that make sense? Are we good? Okay, so that's constantly trying to jack with this. And so we're going to have to like work against it, okay? And so the other issue is that there's another window open. And the other window open is a potassium leak channel. And by the way, there's not just one, there's boatloads of these. Which direction is potassium going to move? Out. Why? Diffusion down the concentration gradient. Okay, so before we go any further, I want just a little gut check. Why will these not move unless you put in a channel? Why can they not diffuse straight through the cell membrane? Charged, exactly, okay? So we're building the cell, okay? So we've got an ideal, we've got something that's jacking with it, and now we're gonna fix it. And we're gonna fix it with a carrier that pumps those ions back where you told them to go, right? So the carrier is going to be the sodium-potassium pump. And I'm not drawing the binding sites because I'm not that good, but we are going to keep track of the directions. So logically, which direction do you need to pump sodium in order to maintain homeostasis? Out, yes? Everybody good? You never need to pump sodium in because it would diffuse in, right? And why would you pay for it if you could get it for free, right? Which direction do you need to pump potassium? In, yes? And in order to get anything to move against its concentration gradient, you need ATP. So every single time this thing moves, I take one ATP, pop a phosphate off of it, and make it into an ADP. Okay? Everybody okay with that so far? Do you see the logic of what you're doing right here? You're restoring homeostasis despite the fact that the windows are open. Okay? All right, so let's add a little bit more detail, and then I'll show you an animation, and then we'll add a little teeny more detail after that. So let's talk about ratios at which this thing runs. So I don't know anybody who calls it the potassium-sodium pump. Everyone I've ever met says sodium before potassium. So sodium-potassium pump, okay? If you do say sodium-potassium pump, I can teach you the ratios really easily of what it moves. It's the 3-2-1 sodium-potassium pump. Every single time it runs, it moves 3 sodiums, 2 potassiums, and uses 1 ATP for the pump. Is that okay? We'll get the Y's of that in just a minute. 3, 2, 1, 3 sodiums, 2 potassiums, 1 ATP for the pump. Okay? All right. Everybody all right so far? Okay. So the question that I ask you in your notes is, okay, I've got this concentration gradient, which is ideal, but sodium and potassium, whenever given the opportunity, will diffuse down their concentration gradients through open channel proteins. Despite the fact that that is true, your body manages to maintain a 15 to 1 sodium concentration gradient, right? 15 more outside for every 1 inside, and a 30 to 1 potassium concentration gradient. And the question that I asked you in your notes, we just answered. How can you maintain this despite these? And the answer is that. Yeah? What is this protein? What kind of protein is it? It's a carrier, yes. And a carrier plus ATP is a pump. I just want you to know that it is not a channel. Okay, so let's look at why it's not a channel. Shape-specific binding sites for the thing that is going to move. That's what she told me makes the difference between those two. Shape-specific binding sites, note, lo and behold, 3 shape-specific binding sites for sodium, right? And then the phosphate, right, the ATP binds and you pop the phosphate off. You use that as the energy source to get sodium to move against its concentration gradient, right? And then when you dump sodium on the outside, at the same time you reveal the potassium binding sites on the outside. Do you see that? You reveal the potassium binding sites. Potassium binds. How the hell do you get that to move against its concentration gradient? Well, that phosphate that was bound from the hydrolysis of ATP falls off, and then you actually get to dump potassium on the inside. So notice that the two, like sodium and potassium, don't move at exactly the same time, but it's coupled, right? Because how many times could you use this pump if you only moved sodium and didn't move potassium? You could use it once, right? It would be useless if you didn't actually reset it. So even though their transport isn't simultaneous, it's coupled, okay? So let's look at an animation of that as well. Okay, so here's your sodium-potassium exchange pump or countertransport pump, whatever the heck you want to call it. So here it goes. You ready? Okay, so 3 binding sites, probably for what? Sodium. Sodium is the pink ball. 2 binding sites, probably for potassium. It is the purple ball. 1 binding site right there, probably for ATP. Exactly. So let's start it. So what we are going to see is the phospholipid bilayer, right? And we've got 3 sodiums bound. How do you get sodium to move the direction it doesn't want to do? Pop off a phosphate. Use that hydrolysis. And then you are going to dump your sodium and reveal your potassium binding sites. Good? Potassium binds. How do you get it to move? Phosphate falls off, moves potassium the other direction, and then once that's over, you're ready to use the thing again. Does that make sense? Over and over and over and over again. And it's just like the freaking balloons in the car. As soon as you stop doing this, you're just going to diffuse and lose your concentration gradients. Okay, it's going to go straight down these channels and lose your concentration gradients. So the logical question that's in some of your minds is, why the hell do you have channels? Why don't you close the damn windows? Well, I will be able to convince you of the necessity of the channels, but I can't do it today because it's actually kind of a long story. Okay, so hold on. So let's go back to the sodium-potassium pump, and then I'm going to tell you one more piece of information. Now, here's something I want you to understand. This is not a memorization thing, because I want to argue that if you truly understand this, you could build it from scratch just starting with these. Do you see that you could do that? Okay, and that's the level of knowledge that I need you to have. So if, for instance, you just had concentration gradients for sodium and potassium, then I could say, okay, which direction would sodium move if you put in a leak channel? And you're like, oh, okay, I can put in a leak channel and then see what it would do instead of memorizing, right? Which direction would potassium move if you put in a leak channel? Okay, I got it, right? And then the next question is, okay, now can you tell me which direction you pump sodium and potassium, right? And you can tell me that, right? Because you can see that I would never need to pump sodium in because it would diffuse in, right? And I need to pump it out to maintain homeostasis. So the level of knowledge that you need is not that I can build this, but that you can build it, right? And you can build it from scratch every damn time, because then there's no trick questions, okay? But now I'm going to throw you a little whammy. If you don't get this part today, I'm not worried about it, because we will cover it again in the next set of notes. But if you can get this part, then the next set of notes gets a little easier, and I do want to at least bring it to you the first time. Okay, so I'm going to tell you just a little bit of extra information about this. This is stuff you will absolutely need to know, and you're going to have a quiz next time. It's going to have this stuff on it too. The charge stuff, I'm not going to quiz you over yet. Okay, so here's something that is also true that I didn't tell you before. What I want you to imagine is the birth of a cell, okay? The cell is a brand new little baby cell. And what I want you to imagine, this is kind of untrue, but it's the only way I know to tell the story that makes sense. Okay, when the cell is born, imagine that there are no channels, but this is true. The concentration gradients are true. Does that make sense? Okay, so all I have at first is concentration gradients, okay? High sodium outside, low sodium inside, high potassium inside, low potassium outside. And the concentration gradients are like this, 30 to 1, 15 to 1, yeah? Okay, and then I also want you to imagine that at the birth of the cell, the intracellular fluid has a net neutral charge, meaning that for every positive, there's a negative something in there. There's no net charge, right? And the extracellular fluid has a net neutral charge as well. For every positive, there's a negative. We'll learn what the negatives are on each place later, okay? So, got it? Concentration gradients and net neutral charge. Now put in channels, okay? Just put in these leak channels, sodium and potassium leak channels. And then I have a question for you. Let's see if you can field it. You're starting at net neutral charge. You put in sodium channel and potassium channel. Which ion is going to leak more quickly? Just look at it. Stare at it for a second and see if you can figure it out. Initially, right? You're net neutral. Which ion is going to leak more quickly? If you think you know, raise your hand. Come on, you can do it. Go ahead. But because why? Because it has a higher concentration gradient, right? And so it's going to leak more quickly. Does that make sense to you guys? Okay, so they're both positive. Started out neutral, neutral, right? Then put in my channels, but potassium is going to leak more quickly initially. Does that make sense? So you're going to leak more positives out than in. Let that go for a couple of seconds, and eventually you will accumulate a charge, right? And so what charge are you going to accumulate on the outside after a few seconds? Positive, yeah, because I'm leaking positives out more quickly than I am leaking positives in. Right? So they're both positive, but I'm leaking them out more quickly than I'm leaking them in. And then on the inside, you're not going to accumulate anything extra, but you are going to reveal something. right? What is the charge on the inside going to be if you leak positives out more quickly than you leak positives in? Negative, exactly. Does that make sense to you guys? Okay, this is the electrochemical. This is the polarized nature of the cell membrane. And now that you've established this, I need to tell you that not only is this homeostatic for the cell and this is homeostatic for the cell, but this is homeostatic for the cell. Okay, it's got an electrical charge difference on either side. And now I'm going to throw you a whammy, which you may hate. It's fine, you'll get it eventually if you don't get it right now. Okay, so we had the birth of the cell. We had nothing but concentration gradients, right? Then we stuck in channels, right? And then when we stuck in the channels, we let them leak. And at first, they just leaked due to concentration gradient. But now we have something else to consider, don't we? The ions will be impacted by the charge that now exists, which, by the way, exists within nanoseconds of the cell's beginning, right? So they leak, and they leak at different rates. So now that the charge exists, wrap your head around one of those two ions is going to increase its transport rate. It's going to diffuse more quickly. Which one? Sodium, because now it's got a concentration and a charge attracting it in the same direction. And which one's going to slow down? Potassium is going to slow down. That will be true for the rest of the life of the cell. Sodium is going to leak more quickly than potassium. Okay? Now let's go back to the 3-2-1. So what does this thing do? It balances out the leak rate after the charge has been established. So it pumps up 3 sodiums, 2 potassiums every time because it's dealing with electrochemical gradient and not just concentration gradient, which is true for damn near the entire life of the cell, right? Because there was just like a nanosecond in which you didn't have a charge and then you did, right? And so now what the pump is doing is it's actually going to, okay, sodium is leaking slightly faster than potassium because of concentration and charge, so I'm going to pump it out at the same rate that it leaks in. Are we okay with that? Okay, all right. So I won't ask you about the whole charge business in this next quiz, but you will be you will need to understand it for the next set of notes. So try to like flip it around, see if you can get it, listen to the recording a couple times. Okay, so does anybody have any questions about like the sodium potassium pump? What I would try to do if I were you is just start with concentration gradients, add in your channels, don't memorize, figure out which direction things are going to diffuse, then add in your pump, and again, don't memorize, figure out which direction things are going to be pumped, right? And eventually you should be able to tell the charge story, but not quite yet. Sometimes that's one thing that people are like I got like 10% of that. I think maybe I'll get the rest of it later. Okay, all right, so we're putting in a whole bunch of work to keep it this way. Like I said, sometimes up to 60% of the cell's ATP is spent on sodium potassium pumps. So I want to give you the first why. Like, why the hell is it worth all of this? Okay, there's a bunch of whys, but here's one. First, can you see that I worked really hard to keep sodium high in the extracellular fluid? And can you see that sodium really wants to move in quickly, right? Now it's got not just a concentration gradient, but also an electrochemical gradient, right? It's going to move in. Well, what if I can use sodium to bring in other things for free because it already wants to come in? So what if I can use it, right? I can take advantage of the fact that sodium's moving in to bring in something that I want to bring in for free, okay? So here's the metaphor. You've got somebody and they're about to drive to the beach in California, right? They're going to the beach in California, and they've got their car all gassed up and packed up. And then somebody says, hey, I want to go to California, but I'm not going to pay for gas, and I'm probably not going to talk to you the whole time, and I'm not going to drive, right? So most of the time, the answer would be, hell no, unless she is the hottest girl imaginable, which is glucose. Glucose is the hottest of the molecules. Then you might put up with those ridiculous parameters, unless you're over 30 and then you're like, screw that, there are other hot women. So you've got this molecule and it wants to go. So basically sodium is already going inside the cell, and I have something that I always want inside the cell. Like, how many hot women is too many hot women on the beach? Like, there isn't a number, right? Like, all of them is how many you want them on the beach. So I want all of the glucose that I can possibly get. Maybe the cell's got boatloads of work to do, and I don't want to have to pay for it, and I don't want to have to worry about the concentration gradient for glucose. Like if there's already a ton of it in, it won't go in, right? Unless you bring it in with something that was going to go in anyway. So this process that we're going to be talking about is going to take advantage of what we just created, right, to bring something into the cell. This process is going to be called not primary active transport, which is what we just did. That is just moving something against its concentration gradient. It's going to be a two-step process. Secondary active transport. The first part is not active, doesn't require any ATP, and the second part does. And I've got an animation for you, but you have to listen carefully to this. So what I am going to do with secondary active transport is I am going to use sodium's electrochemical gradient, which favors it moving in. And instead of move it through a channel inside the cell, I am going to move it through a carrier that has a binding site for sodium and a binding site for glucose. And then I'm not going to use ATP, I'm going to use the electrochemical gradient for sodium to bring glucose inside the cell. Does that make sense? It's basically like you put in all the work on the front end, right? And you were already going to the beach, right? And then she just sits in the car and goes to the beach with you, right? Because you were already going that way anyway, right? You already paid for the gas, you already packed the car, you already did all the crap, right? So what's going to happen is this, I wish it were a better picture because it actually has a binding site for sodium and a binding site for glucose, and it won't actually move until both binding sites are taken up, right? And then it moves it in. And it will move glucose inside the cell even if there's already a boatload of glucose inside the cell. It basically doesn't have to pay attention to concentration gradient. Otherwise, how would you get glucose inside the cell if glucose were high inside the cell? You'd need to pay for it, right? You'd need to pump it. This allows me to not have to pump glucose inside the cell. Does that make sense? Okay, so what I'm going to do is the first step is using a carrier protein. I can't use a channel for two reasons. Any idea why? Glucose is too big, yes. And also, are channels specific about what they carry? No, they're not specific, right? They're kind of like willy-nilly, like I kind of like sodium, but any positive ion. So this is a shape-specific binding site, right? So it binds sodium, it binds glucose, it brings both of them in, okay? But of course, if you do this enough, you are going to disturb your sodium concentration gradient. Yes? And what would you do to fix it? After, for instance, you brought in 1, 2, 3 glucoses with sodium. What are you going to have to do? What do you have to do to sodium? You're going to have to boot it back out. You're going to have to pump sodium back out. So let's go back to the meaning. So this is secondary active transport because the first step is not active. That's just facilitated diffusion with a hitchhiker, right? That makes sense? Okay. But the second step is active, which is the sodium potassium pump. Okay. So now let's compare cost savings analysis on doing this versus pumping pumping glucose. Okay, so let's say we had the same situation. We have a cell that has a bunch of glucose, but has boatloads of work to do, so it knows it's going to need more glucose. You can pump glucose inside cells. You can, right? You can use one ATP to bring one glucose in, another ATP to bring another glucose in, another ATP to bring another glucose in, right? But this is 2/3 cheaper, isn't it? Right? Because you get to bring in 1, 2, 3 before you spend 1 ATP. Does that make sense? So this is secondary active transport. And basically what you are doing is you are taking advantage of what you just built in order to get things that you need inside the cell. We use this to bring glucose inside the cell. We use it to bring amino acids inside the cell. Let me show you an animation that will give you a visual. And it is this one. Okay, you guys ready? So let's start from back here. All right. So what I have is I'm bringing in sodium and something attractive, like sugar. Other sugars come in this way too. And so what I'm going to do is I'm going to continue to do this. And the only thing I don't like about this is that it doesn't show the shape-specific binding sites, but it does have shape-specific binding sites. Okay, people, what kind of protein is this? Carrier. That is a carrier protein, yes. So I'm bringing in, and then eventually what's going to happen is I will jack up my concentration gradient for sodium, and then I'm going to have to do the next part, which is I'm going to have to pump sodium out. And I'm going to use the sodium potassium pump that we already learned in order to do that. So concept check question. What if I didn't fix my sodium potassium? What if I didn't fix my sodium concentration gradient? Do you see that what would happen is I could do this a few times? After I got to like 25, can I use this transport mechanism anymore if I've screwed up my sodium concentration gradient? No, right. So I have to fix it or else I can't use this transport mechanism anymore, or any other transport mechanism that depends on sodium's concentration gradient. Does that make sense? So what I'm doing is I am actually using sodium's concentration gradient to move something, right? Because I kind of already paid, right? I paid on the front end for sodium's concentration gradient. FYI, although it's a little harder to picture, you can also use sodium to bind, and sodium comes in and you can use it like a revolving door to pop something else out. So you can use that like this. So if you don't want to pay to get calcium out, you can use sodium to move the door and actually get calcium to move out, right? This is instead of using ATP. This is also used to get H+ ions out at the kidneys. So basically, instead of using ATP, you're using the electrochemical gradient that you already created. Is that okay? So this is secondary active transport. One more time. First step is really what kind of transport? Facilitated diffusion, right? With a buddy, right? And then the second step is active transport, right? Okay, so now let's compare. Which one would be cheaper for getting sodium inside a cell if the cell already had boatloads of sodium? Primary active transport or secondary active transport? Yeah, secondary is cheaper, right? So this mechanism exists for a reason. You guys are all right with that? Not do you love it? Because everybody hates secondary active transport, but you run into it all over the body. It's basically like you're just taking advantage of stuff that already exists, right? So you're going to see it a lot this semester. Does anybody have questions? For some reason in phys this semester, like people just are not asking questions. I think you all need more caffeine. I think that's what it needs to be. Go ahead.
During the animation, I saw that you use sodium potassium pump in more potassium.
Yeah, it just leaks right back out of leak channel. Yeah, it doesn't really mess with anything too much. It's just the sodium potassium pump really never moves sodium without also moving potassium. And that's the one that you have on all of your cells. But that's a good question. Okay, so we have, this is, by the way you get amino acids inside cells. This is also one of the mechanisms to get glucose inside cells. FYI, don't get confused that I've moved sodium like this and then moved sodium like that, or glucose moves in with insulin, right, as the transport mechanism, or with sodium. Not surprisingly, there's like 15 different ways to move glucose because it's freaking important, right? There's also a lot of ways to move sodium. So I'm not teaching you one thing and then overturning it. I'm teaching you multiple mechanisms. And then what we're trying to get to, and we'll work on it, we'll get most of the way there today, is we're trying to figure out when you would use one versus the other, okay? So they're not mutually exclusive. You're gonna learn 5 or 7 ways of moving glucose by the time the semester is over. Okay, so for those of you who are table people and like to do comparison contrast and figure out, there's this table in your textbook, table 4.2. Table 4.2 actually compares the transport mechanisms and says, okay, which direction is the thing moving? Does it use a channel? Does it use a carrier? Does it use an energy source? And if it does, is it ATP or the electrochemical gradient? So my brain is a table brain. My brain is like an organization scheme brain. Most of my students are very visual, though. So a lot of you guys are animation brains, but I am like a delineate, separate, make like a freaking spreadsheet out of it kind of brain. But I realize that a lot of you guys are not that way. And when I realized that, I had to completely change my teaching mechanisms because I am not a picture person. But I do this for you guys. Like, I don't do pictures. I take a picture and immediately make it into words and then never look at the picture again, ever. And I don't look at animations except for once. I'm like, oh, it's fine. I got a story about that. We can tell a story. Okay, so last types of transport are vesicular transport. Okay, so you've met these before. You may not have referred to them as vesicular transport, but basically what we are doing with these is we are moving something across the cell membrane by using a vesicle. Yeah, and remember a vesicle is just a plasma membrane bubble, right? And so where do these fit into the whole cheapest, fastest prediction Vesicular transport is the most expensive and the slowest form of transport. So if you are transporting something by endo or exocytosis, you need to be able to defend why you didn't do it another way, right? That makes sense? So it's super slow and it's incredibly energetically expensive. And you've met it before, so let's just talk about endo and exocytosis. With endocytosis, of course, what we're doing is we're bringing things across the cell membrane that couldn't get across any other way. Let's start first with phagocytosis, which is bringing in solid chunks like a whole cell. So imagine that I am a white blood cell and this is my phospholipid bilayer, yeah? Okay, this is a coccus bacteria that I'm about to do endocytosis on, phagocytosis, and then whoop up on with the lysosome, right? So how do you do it? The way that you do it is you take advantage of the fluid mosaic nature of the cell membrane, and what you do is you fold this cell membrane up around the bacterium, right? And then because of the fluid mosaic nature, as soon as they touch, they actually seal, and then you bring the bubble on the inside, right? And then you fuse it with a lysosome and you whoop up on it. You didn't gain or lose any phospholipids in the process, right? So the question, of course, which you should be able to answer, is why didn't you move it straight through the cell membrane? Too big. Why didn't you use a channel? Too big. Why didn't you use a carrier? Too big. So it's too big for any of those, right, mechanisms. So you had to do plan Z, which is endocytosis, right? Okay, so specifically it's phagocytosis when you take in solids. It's pinocytosis when you take in fluids. And then the slowest of all the slow is receptor-mediated endocytosis. So let's talk about that one, and then we'll move on to exocytosis. So with receptor-mediated endocytosis, I am looking for a specific molecule that I cannot get across by any other mechanism. There's a couple of forms of iron that you have to use this for, and a couple of forms of like cholesterol that are not completely lipid soluble that you have to use this for. It's not a really common transport mechanism. And what it is you are looking for these little purple triangles, right? And they can't get across by any other mechanism. So what I need to do is I need to wait for the little purple triangles, let's say they're iron, to bind to receptors, yeah? And after they have bound to X number of receptors, that's what will trigger endocytosis. You with me? Why not just do endocytosis when you get one bound? Yeah, it's too expensive to move like one purple triangle, right? So you have to wait for them all to bind to the receptors, and once they bind to X number of receptors, it triggers endocytosis. So do you see why this one is the slowest of all of them? Because not only do you have to do endocytosis, but you have to wait for something specific to bind to the receptor. So this is called receptor-mediated endocytosis. It is slow and expensive, okay? And you wouldn't do it if you could do it any other way. And then last but not least is exocytosis. And exocytosis is easy, and you've learned about it in other classes, but let's put a human spin on it, and let's say I'm a pancreatic cell, I just made some insulin, I'm super duper proud of my insulin. Insulin is a large-ish protein, it's not like ginormous, but it's pretty big. And where did I make that insulin inside me? Where do you make proteins? You can do this, I know you can. Where do you make proteins, guys? What? Nope, mitochondria makes ATP. Yeah, the rough ER. There you go. High five. You're my favorite today. The rough ER. Okay, so now I've made this protein on the rough ER, but I need to package it in a vesicle. I'm going to do it again. Where you package stuff? You're my new favorite. Golgi apparatus. Yes, Golgi apparatus. So you package it in the Golgi apparatus and you package it in a vesicle, right? So now I've got this protein in the vesicle, but I need to get it out or it won't do anybody any good, right? And so what I do is I've got this protein, too big, too big, too big, too big to do any other mechanism. So what I do is I take this vesicle and I smash it up against the cell membrane, and when I smash it up against the cell membrane, it takes advantage of the fluid mosaic nature of the cell membrane, right? And what I do is I end up dumping the insulin. Do I even lose a phospholipid? No, they just become part of the cell membrane, right? So you're just like moving them from the Golgi to the cell membrane, right? That's exocytosis. You wouldn't do that if you could get it out by any other mechanism because it's pokey and expensive. Okay, that makes sense? Okay, so now let us, phagocytosis, pinocytosis. Let's see if you guys can do this. So wake up. We're going to see if you guys can do application now. Can you apply these things? And I promise I will be super nice to you if you give it a shot. I promise. Okay? So in each of these situations, I'm throwing a scenario at you, and I'm going to ask if you can try to figure out how you would accomplish this transport. And so how would each of these substances cross the cell membrane? And why? Why are you using that transport mechanism? And if it uses a protein, you need to be able to tell me whether it's a channel or a carrier or a pump, which is a carrier plus ATP. Are we okay? You there? Okay. So oxygen is diffusing across the cell membrane down its concentration gradient. Anybody want to hazard a guess? You have to raise your hand as to what type of transport it's going to use.
Diffuses right across the membrane.
Yes. Why can it do that? It is neutral. It is lipid soluble. Yeah, because it's like a non-polar, right? Lipid soluble molecule. Everybody okay with that? Yeah, and it's small too. Everybody okay with that? So that's how oxygen gets in, and that's just true. That's how oxygen gets in your cells. Okay, so let's try the next one. I've got potassium, and it's diffusing across the cell membrane down its concentration gradient. What transport mechanism? Channel, okay. Now that's the protein, but what is the transport called? What's it doing through the channel? It's diffusing, right? It's just diffusion through a channel, right? So here, let's back up one, and you guys know this, but I want you to start to be able to say it. Why can't it do simple diffusion across the cell membrane? Charge, right? So it's charged, so it does diffusion through a channel. Yeah, you good? Are you getting there? Okay, next question is, I have an amino acid that is moving into the cell for protein synthesis. How are you going to transport it? Carrier, I totally agree with you. Carrier. What do you call diffusion through a carrier? Facilitated diffusion. Now let's throw you a little whammy and say that there's already a whole bunch of amino acids inside the cell. Now what do? How do I get something inside the cell without paying for it directly? Secondary active transport, right. I could use a carrier if its diffusion, if its concentration gradient favored it. If its concentration gradient didn't favor it, the next cheapest thing would be to use secondary active transport and bring it in, for instance, with sodium. Does that make sense to you guys? Okay, but it's still a carrier, by the way. Okay, let's back up just one, and it is an amino acid. Why, she got it right, why not a channel? Too big for a channel, right? Okay, are you hearing the logic that I'm like trying to get you guys to do? Okay, it's annoying, but you will actually build it, and then it's not my knowledge, it's your knowledge, which is what we want. Okay, next one. A large antibody protein secreted by a white blood cell. Large antibody protein secreted by a white blood cell. Exocytosis. Okay, defend your position. Why do you need to use exocytosis instead of a channel or a carrier? Simple diffusion.
Is what now it's getting rid of it. From like the Golgi like put it up in that.
Golgi puts it up, but why can't you put it through a channel or a carrier? Too big, exactly. It sucks. Good. Okay, we're almost done. It's painful, but it's like medicine, right? You're like, it's fine. Water moving from a cell's ICF into a highly concentrated saline solution. Osmosis, exactly. Yes, it's osmosis, which is, by the way, just a special instance of diffusion, right? It's diffusion of water across the membrane. Okay, last one, and then I'll stop for a minute. Okay, calcium being pumped into the calcium-rich ECF to allow for muscle relaxation. Calcium being pumped into the calcium-rich extracellular fluid. You need a carrier and ATP, so you need a pump. What do you call it when you pump something? Primary active transport. Exactly. Okay, so do you see that the logic process, you can start to use it? And the idea, hopefully, is that at some point in the near future, you get past rote memorization and start to have application. Start to like say, oh, okay, I have a prediction, right? And it's not terrible if your prediction is wrong, because then you just like fix your data, right? And then you like have better predictions for the next time. That's what I want for you. I want you to be able to say, okay, I think I can hazard this one, and you're like, oh, okay, that was right. Or, oh, okay, it was wrong, but here's why it was wrong. right? And then you learn, okay? So, all right. So now what we're going to do is we're going to take this. Yes, sir.
Can you also look at it just anything other than sodium potassium needs some type of transport mechanism?
Anything other than sodium and potassium? You mean in all ions too? Or anything bigger?
Anything bigger.
Yeah, if it's bigger than sodium or potassium, you're going to have to probably use a carrier or endo or exocytosis, right? Anything bigger than an ion is going to have to use one of those, the carrier, endo or exocytosis. So yeah, that's true. Yeah, they will. I mean, unless it's a big lipid, right? A big lipid can do whatever the hell it wants. It's just like, I'm estrogen. I'm a big fat lipid, and I will go wherever I want, right? Straight into your brain and make you act crazy. Testosterone does it too. Don't think we don't notice. My little 11-year-old's about to hit puberty. I'm dreading it because he's so sweet right now. It's going to happen. Okay, so here's an application. So here's what we're going to do. We are going to take these and we're going to try to use our predictive mechanisms to try to figure out how the hell you absorb things across your intestinal epithelium. And it will be a combination of these things. So here's what we're going to do. We're going to eat some Cheetos and try to figure out how we get the sodium all the way into our bloodstream. We're going to eat a Snickers bar and try to figure out how we get the glucose all the way into our bloodstream. And then we're going to drink some water, right? Because we got to do something healthy in this story, right? We're going to drink some water and figure out how the water gets in. Does that make sense? So what we're going to do is we're going to call this epithelial or transepithelial transport. Because you guys know in order to get something into your bloodstream, it has to cross an epithelial tissue. Yes? And your epithelial tissues, remember, have this characteristic. So, by the way, where in your digestive tract do you do the vast majority of your absorption? Okay, so this is where we're going to be. We just ate Cheetos. We're going to do Cheetos first. And we are going to have to get the sodium from the Cheetos into our bloodstream, right? And why the hell do we need sodium? Well, that's part of the story right there, right? We need sodium. Most of us are not sodium deficient because we live here, right? So we got no problem getting enough sodium. Okay, so in order to do that, we are going to have to do transport multiple times. So stick with me and then we'll do sodium specifically. So we're going to have to go from the lumen of the small intestine. Do you remember what kind of tissue lines the small intestine? Simple columnar epithelium with what on the surface? Not cilia. Microvilli to increase transport. Yes? Okay, so we're trying to get it across. We're going to have to cross here. There's going to be a transport mechanism that you use to get across the apical surface. Yes? Then we're going to diffuse through the intracellular fluid. Yeah? Then we have to use a transport mechanism to get across the basal, or your phys book calls it basolateral, but it's the same thing. Basolateral surface. And then the basement membrane is no problem because it's basically just like proteins and sugars and stuff. Then we're going to go through the interstitial fluid, and then we have to get it into the bloodstream. But luckily, we don't have to worry about transport into the bloodstream because this is a fenestrated capillary. What does that mean? It's got holes in it, right? So as soon as you get it close enough, it's going to go straight in. Fenestrated capillaries are really logical to put right behind your digestive tract, right? Because they need to like suck up stuff. Okay, so here's what we're going to do. We are going to try to predict how sodium is going to get here, 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 and here. So let's do sodium first. Okay, here's sodium. We just ate some Cheetos. We want to absorb sodium into our bloodstream, but we are going to have to cross it here, and we're going to have to cross it here before we can get it here. So first question is, what do you predict about the transport mechanism that you will use to get it across the apical surface? Give it a shot. What'd you say? Diffusion, but you can't diffuse straight through, right? What do you have to use? A channel, right? And so how do we know that it will diffuse? What do we know about sodium's concentration gradient in here? It's low, yes, right? And we work to keep it low, right? So sodium is going to diffuse through a channel across the apical surface. Does everybody understand why? Okay. If you don't, why can't you get it straight across? Charge. It's not going to move straight across, right? And it's small enough to move through a channel. So that's the next cheapest, fastest thing. Everybody okay with that? So now we got it inside the cell, but that's not in the bloodstream. Now we have to get it out of the cell, okay? So now we have to get it to move across the basal or basolateral surface. But we got an issue, man, because what's the sodium concentration in here? Low. What's the sodium concentration out there? High. How do you get it to move? You have to pump it, exactly. What kind of protein is that? Carrier. Carrier plus ATP is a pump. What is this transport mechanism called? Primary active transport. Yes, primary active transport. And to address the question you asked before, what about the potassium? The potassium moves sodium out, potassium gets pumped back in, and it just leaks right back out. Not really a big deal. Everybody okay? And then how do you get it into the bloodstream? All you have to do is get it high here, and it gets picked up by the blood plasma because it's a fenestrated capillary. Do you understand? Okay. So let's try something harder then. Okay. Now we are going to eat a Snickers bar, right? And we are going to try to get the glucose into our bloodstream as cheaply as we possibly can, right? And how much glucose do you want to absorb? All of it. It's like money, right? So you want to absorb all the glucose if possible. It's not always possible, but that's what your body tries to do. It's an incredibly valuable chemical. So here is the story that we're going to tell about glucose. Ready? Okay, so I just ate a Snickers bar and I want to get glucose inside the cell despite the fact that the cell might already be chock full of glucose, right? I don't want to have to pay attention to glucose's concentration gradient. So how do I do that in the cheapest way possible? Secondary active transport, yes. Okay, so what I am going to do is, by the way, any sugar worth a crap always has salt in it. Have you ever not put salt in your chocolate chip cookies? They taste like butt. They taste terrible. You always have to have a little bit of salt to make sugary things taste good. So generally there's a little bit of salt in everything sweet that you eat. And so what you are going to do is you're going to take advantage of that. And so now I have the electrochemical gradient favors sodium moving in, but this time it's bringing a buddy, right? And everybody's happy to see glucose, right? So it is actually going to bring glucose in. So here's the question. What is this protein? It's a carrier, yes. And the first step of secondary active transport is really facilitated diffusion, right, with a buddy. That makes sense? Okay, so now let's just follow glucose until we get it into the bloodstream, and then we'll take care of the sodium, okay? So let's follow glucose. Now I've got glucose in here. And the only thing you need to know in order to figure out what to do next is that I never leave glucose in high concentration out here. I'm always carrying it away because you know it's needed somewhere, right? So glucose doesn't really stay high in the extracellular fluid. So that gives you the concentration gradient that you need. So now I have high glucose here, relatively lower glucose here. How am I going to get it out? Carrier. And what's that transport called? It's called, what is it when you diffuse something through a carrier? Facilitated diffusion. It's just not bringing a friend this time, right? It's just facilitated diffusion. So now I got glucose in the interstitial fluid and it just gets picked up into those fenestrated capillaries and then it gets to go do its glucose job. But of course, after you do this 1, 2, 3 times, you have disturbed the concentration gradient for sodium, yes? And then you have to fix it. So what do you have to do? Yeah, you have, well, it's primary if it's by itself. When you put it together with that one, it's actually called secondary active transport, but definitely active transport, right? You have to do active transport and you have to pump sodium out, right, to restore the concentration gradient. So one more time, what kind of protein is this? It's a carrier. Yes, carrier plus ATP is a pump. Yes, that makes sense? Okay, so this step plus this step is secondary active transport. Yeah? So collectively, they are secondary active transport. Is that okay? Okay, so this is the why. This is why you put all of this effort in. This is why the hell I'm torturing you with transport mechanisms that you learned in 1610. Because eventually I want you to be the person who figures out, oh, this is how you absorb something at your digestive tract. This is how you get rid of something at your kidneys. This is how you do whatever, right? Does that make sense? Okay, so last one is now we are finally going to drink some water because we went on a bender. We had some Cheetos. It was a bad day, right? We had some Cheetos and we had a Snickers bar in the same day, and we are over the age of 11, right? If you are under 11, that's a good day, right? You're like, everything is going right in my life. So if you are over, you're going to feel bad about it, right? Especially if you're over the age of 30, because you're like, oh my God, it's going to take me like 72 hours to burn that. That's terrible. Okay, so now we need to absorb some water. Your textbook has a crappy picture of this, so I just have to flail my arms around and show you. Okay, so here is how you absorb water at the intestine. I'm going to drink water. I also ate some stuff just recently, and so what I have in my lumen of my intestine is I am moving sodium. So I've been moving sodium, right? And so here's what you have to think about. When I move sodium, and there's sodium in damn near everything you eat, there are ions in damn near everything you eat. So what I'm going to do is I'm going to take sodium, and by one mechanism or another, I'm going to take it from the lumen to the intracellular fluid, yes? Then I'm going to take it across the basal membrane to the interstitial fluid and then into the blood plasma. So with any ion, this will work, but think about sodium for a second. What happens to sodium is you move it from one place to the next, but as you increase the sodium concentration in the intracellular fluid, what do you do to the water concentration? If you increase the sodium concentration in the intracellular fluid, what do you do to the water concentration? You decrease it, yes? And then water will diffuse down its concentration gradient, right? So it will do osmosis, right? And now as I move sodium from the intracellular fluid to the interstitial fluid, yeah, you increase the sodium concentration. What do you do to the water concentration? You decrease it, right? And then you move it into the blood plasma. So do you see that what you're doing is you are creating an osmotic gradient, yes, for water as you are moving solutes through, okay? So it's just osmosis. As you absorb solutes, so you absorb water, right? My phys professor always said that solutes suck, right? And sodium sucks the most, right? It's like sucking stuff in, which is why, for instance, if you have hypertension, chronic hypertension, and your blood volume is one of the things that can increase your blood pressure, what do they say that you should probably do to your diet? You should stop eating so much sodium because it's making you actually absorb and retain water. Does that make sense? Or just eat a 1 pound bag of Cheetos all by yourself because you've had a shitty day. And then wake up the next day and figure out that you can't actually take off your rings. Like, oh my God, and apparently I went up a pant size. What the hell's going on here? It's water retention because solutes suck and sodium sucks the most, right? So it is basically osmosis that you are using to bring water in. Everybody okay with that? Okay. So when you have your test, and you're not going to have it until a week from Thursday, you will have to explain to me either in words or in very well labeled pictures, because please remember that I am not a picture person, so it has to be super well labeled. One of these three. You are either going to have to explain transepithelial transport of sodium by itself, transepithelial transport of glucose, or transepithelial transport of water, right? Okay, you're going to have to explain one of those. Okay, so last thing is filtration. Okay, so your textbook doesn't talk about filtration until it gets to the kidneys, but to me, filtration is just another example of moving something across an epithelium. So filtration you've learned about before. Filtration is basically, doesn't give a crap about concentration gradients. It's not active transport. What it cares about is pressure gradients, okay? So if I have high pressure and then a membrane and then low pressure, and then the membrane has holes in it, what is going to happen is I am going to push things through the hole. Anything that fits through the hole will get to go through, and that is filtration. So this happens all over your body because there is a difference in pressure between the fluid of your blood plasma and the fluid of your interstitial fluid. Yeah? Which one's higher pressure? Blood plasma or interstitial fluid? Blood plasma, why? You got a freaking pump hooked up to it, right? It's always going to be slightly higher pressure. So what's going to happen is that your capillaries have varying levels of porosity, like some of them are pretty impermeable and some of them are fenestrated and some of them are like sinusoid capillaries with big old holes. And so what's going to happen is you are going to push things through the holes from high pressure to low pressure, and you don't give a crap about concentration gradient. So this is filtration. Of course, they teach about it in your kidneys, but it happens at every capillary in your body. The metaphor that you can use, it doesn't work quite as well in Utah as it did in Texas, but it's making coffee. So if you want to make coffee, you can talk about filtration because that's actually what's happening. You can call it a coffee filter. So if you're making typical drip coffee, what you're going to have is you're going to have a membrane, a coffee filter, that has some level of permeability, right? You don't want it with holes this big, otherwise you get big coffee gross chunks. You want it with some level of permeability, and then you pour water in, coffee's on top, you pour water in, and it will pull things through just based on size, right? So it pulls coffee through based on size and water. So with filtration, water always moves and it pulls anything that will fit through the holes. So it's different than osmosis because it's not just water moving, right? And it's also not concentration dependent. So when you're making coffee, if you put dirt in a coffee filter, would it also move dirt? Would it also move red Kool-Aid? So it's not at all specific about what's moving. And it doesn't give a crap about concentration either. You could fill the entire pot with coffee grounds and it would still do filtration, right? It would still do it. So what you're using is hydrostatic pressure of high pressure of water to low pressure of water, and it's pulling through anything that will fit through the holes. So we use filtration dramatically all over the body. It's used in your capillaries. Of course, it is massively used in your kidneys because your kidneys have high surface area of their capillaries. Big holes everywhere, so it's good for filtration. And then the kidneys bump up the pressure, right? There's a little pressure bump in every single nephron, so they're really, really effective at filtration. Your kidneys filter multiple times your blood volume every minute. But the rest of your capillaries in your body also are doing filtration. So filtration is not selective at all except by size. No ATP is required because you generated the pressure elsewhere. Big things like whole proteins should not cross. But if you hooked up a fire hose behind a coffee filter, could you get a bowling ball through? Yes, once. This is why I want you guys to start to conceptualize what will happen to the kidneys with chronic untreated hypertension. So if I have chronic untreated hypertension, I start to push accidental things through at my kidneys. I get proteins in my urine. Sometimes I get whole blood cells in my urine. And all of those are indications that you've hooked up a fire hose behind the thing. Chronic untreated hypertension can cause kidney failure because you're actually busting through all of those filtration membranes. Does that make conceptual sense to you? Okay, so big things shouldn't cross. So in the kidney, it's basically the blood pressure. Elsewhere in the body, you're doing it with every capillary. So let's just do one last little tidbit, and that is, okay, let's talk about what should happen in your kidneys, and then what happens if your kidneys are not working properly. So what your kidneys should be doing is, you probably learned nephron structure and anatomy, and I'm not going to do it in much detail yet, but what I want you to know is at your kidneys, you are going to have two sets of microscopic porous tubes. One of them is going to contain blood, so this is basically a capillary. And the other one's going to contain urine. It's actually called filtrate for a while. And both of them have some level of porosity. Yeah? Okay. So what should happen in a healthy person is that filtration should make you get rid of waste products. Yes? So this top picture is going to be healthy. And let's concentrate on a waste product that we all know exists in the urine, right? So you should be filtering out urea, okay? Now, that's a healthy person. What about a person with kidney failure? Their filtration mechanisms will fail, and then what will happen to the urea concentration in their bloodstream? It will increase. Does that make sense to you? Okay, so if this fails, if filtration fails, then you can do a mechanism called dialysis. Dialysis is not the same mechanism. By the way, this is filtration. This isn't a healthy person. Okay, now we run into an unhealthy person, and an unhealthy person has kidney failure for whatever the hell reason. Diabetes is famous for causing kidney failure. And so what happens is with this, we are going to take the blood out, and we're going to send it through a dialysis machine, and then send the blood back in. So we're going to do hemodialysis. We're going to take their blood, and we're going to send it through a dialysis machine. This is what was supposed to happen, and then this is what's going to happen. Okay. The dialysis machine has a little chamber in it called a dialysis chamber. And I've got one in my office. I just forgot to bring it. And so what's going to happen is this dialysis chamber is two-sided, and it has a super curved membrane, basically to increase surface area. And so what you're going to do is you're going to send blood in, funky, dirty blood with a high concentration of urea, or else you wouldn't be doing this. and then you're going to put the blood back into the patient, okay? And we hope that the mechanism will get rid of urea during the process, okay? And then I'm going to use counter-transport exchange, because I don't know if you guys remember enough of chemistry, but you actually get better exchange if they're going two different directions. So what I'm going to send in this side is a dialysis solution, yeah? And then I'm gonna dump it into the garbage, toilet, whatever the hell they dump it into. Okay, and I'm gonna continually put fresh stuff in there. The idea is that I decrease the concentration of urea in the bloodstream before I put it back in. And in order to make that occur, I need to make this membrane, this is a dialysis membrane, permeable to urea. Yes? And then what should I do with the dialysis solution? What about its concentration of urea? 0, right? No urea at all. So basically what I'm doing is I am putting the blood in with a high concentration of urea. It runs by this membrane that is permeable to urea, right? This has a low concentration of urea. What happens? Where does urea move? It moves in, yeah, to the dialysis solution, and then I dump it. And then I continually put fresh dialysis solution in, sometimes for hours at a time, if you're actually having to go through dialysis, 4 or 6 hours at a time, cleansing your bloodstream. Does that make sense? So what I'm doing, and then I put the blood back in. Sometimes they do it out one arm and in the other. Sometimes they do it out one arm and then back in the other one, or back in the same one. But there's a couple of other things. By the way, this is a simplified version. You can also cleanse other things out of the blood as long as you make it permeable to these things. But we better make sure something about the tonicity. We should probably make sure that the dialysis solution is blank tonic to the blood. Isotonic to the blood, right? Otherwise, what will happen is you will get crenation of blood cells, or you will get potential hemolysis of blood cells. So you make an isotonic solution, you make it permeable to all the bad stuff. You don't make it permeable to the good stuff that you wanted to lose from your bloodstream, like glucose, right? Right? And then you can basically engineer what's happening. And they do actually different dialysis chambers based on the chemistry of the person's blood. Does that make sense? Okay, so last little tidbit. In your body, getting rid of urea is based on filtration. But in the dialysis situation, or clinical situation with dialysis, it's not based on filtration, it's based on what? What is this? That's diffusion, isn't it? Yeah, it's just diffusion. Good? Okay, and however long you have to do that depends on how badly your kidneys are failing. At the end of serious kidney failure, you can have to be doing hemodialysis for 6 hours a day. You are on your last leg when that is happening. Really, really common with type 1 diabetics. All that sugar that you're constantly delivering to your kidneys ends up damaging your filtration membranes, so it's really, really hard on your kidneys. Okay, so I won't ask about filtration on your quiz because I haven't taught it to the next class yet because the doors were locked. We couldn't get in a damn room. So there are 5, don't even. This is after we've already sent letters to the provost and everything. So I won't ask about this yet. I won't ask about filtration or dialysis yet. It won't be until later. Okay, so you got a quiz that'll be at the beginning, assuming we can get in. It'll be at the beginning.
On Thursday?
On Thursday, yes. Quiz on Thursday and then test the next Thursday. Do not miss Thursday. It is one of the hardest lectures to do on your own.
What specifically is the quiz on? Like you were just saying?
It's over this set of notes. It's cell transport, not homeostasis. We already did that. Okay.